All right, thank you very much, and thank you to the organizers for the chance to speak. So suppose we have a quantum system with n pieces. The wave function for this system is an enormously complicated object with an exponentially large number of components, exponential in system size. So this wave function contains an enormous amount of quantum information. And there's been a surge of effort over the last 10 or 15 years in understanding how that quantum information is organized. First in condensed matter, and more recently in high energy. So in a random wave function, there's no particular structure to the organization of quantum information. But we don't really care about random wave functions. We care about reasonable states in reasonable theories. So I want to ask how quantum information is organized in ground states of systems with a local Hamiltonian, in energy eigenstates, again with a local Hamiltonian, in thermal states, or maybe in states that are far from equilibrium but evolving under local interactions. So in systems like that, there's a lot of structure to the quantum information. And a useful way to characterize it, because the system is local, is by asking how the different subsystems are entangled with each other. So the simplest thing we could do is calculate the entanglement entropy of some single subsystem A. But entanglement is really a many-body phenomenon. So we'll get a lot more detail by calculating, say, the mutual information of multiple disjoint subsystems, or by separating it into even more than two subsystems and constructing more elaborate measures of the information relationship between multiple subsystems. So if we could calculate the entanglement of every subsystem with every other subsystem, then we could map out how quantum information is stored in this wave function. An entanglement entropy of every possible subsystem maps out the storage of quantum information. And in local systems, as I said, this map that you create this way, both in static states or the dynamics of the map, will have an intricate structure. So this is not something that we ordinarily measure directly in experiment, but in a way it's something more fundamental. The entanglement provides sort of a background arena for all of the more detailed questions that you might want to ask, like the value of local correlation functions. So you could ask, somebody asked me last week, why does everyone care about entanglement entropy so much? And my answer is, well, it's not a local correlation function. Why don't we just talk about correlation functions? So my answer is the same reason I care about the distance between 2 points. That's not a correlation function, but it conveys a great deal of information about how the physics at those 2 points is related. So entanglement is sort of reminiscent of geometry already in any quantum system. But in holographic theories, this isn't just an analogy. The entanglement is closely related to emergent geometry. So this is evident in Maldasena's formulation of the eternal black hole, and especially in the holographic entanglement entropy formula introduced by Ryu and Takenagi. So to the extent that to the extent that geometry is related to entanglement, that means that gravity is a theory of entanglement dynamics. So this has to be true in some sense, according to ADS CFT. But can we actually derive this from quantum field theory? So what I'll describe in this talk is, first of all, several interesting situations where the answer is yes, in two-dimensional conformal field theory and 3D gravity, where we can actually get nonlinear gravity out of entanglement dynamics. Higher dimensions is harder. I may come back to that with a few comments at the end. And then I'm going to turn this around and try to extract some lessons from these gravity-inspired methods to learn some new results about non-holographic 2D CFTs, so actually CFTs that are very far away from anything at all holographic. So this is mostly based on these two papers with Curtis Asplin, Alice Bernamonte, and Federico Galli. So here's the setup. We're in 1 + 1 dimensions. So space is a line, and that means that subsystem A consists of one or more intervals. The other option is to put the theory on a circle. So subsystem A is a segment of the circle. For our purposes, I'll always take the full system to be in a pure state, rho equals psi psi. And then we want to calculate the entanglement entropy, which is the von Neumann entropy of the reduced density matrix in region A. I'll start by giving some flavor for how we calculate these entanglement entropies in holographic conformal field theories in 2 dimensions, and then talk about some applications. So there's a log in the entanglement entropy, and logs are sort of tricky to deal with directly. So we use a replica trick, which is to replace that with a power, trace of rho to the 1 plus epsilon, and then extract the entanglement entropy by taking epsilon to 0. This power here basically introduces a conical defect at the edge of your region A. And what that means is that entanglement entropy is computed from a correlation function of these conical defect operators in the limit where the defect goes to 0. This defect sigma is called a twist operator. And as the defect goes to 0, it has conformal dimension c over 12 times epsilon. This is a replica trick of Calabresi and Cardy. I'm being a little schematic. What we actually do in practice is to compute this for integer epsilon and continue to epsilon equals 0. OK, so it's related to this correlation function. But in general, these correlation functions can't be calculated. If there's more than 2 operators in there, then the correlation function will depend on the full details of the conformal field theory. But holographic CFTs are special. We don't know exactly what the criteria are for a theory to be holographic, but we know that it has to satisfy at least 2 properties. First, it has to have large central charge, c much greater than 1. And second, it has to have a sparse spectrum of low-dimension operators. So the first is necessary for the ADS radius to be large in Planck units so that you get a semi-classical theory. And the second is necessary so that you have a reasonable effective field theory on the gravity side with some finite number of fields. So there are several interesting states, at least, where in theories like this, satisfying these 2 conditions, the dominant contribution comes actually from stress tensor exchange and stuff that you can build out of the stress tensor. In other words, in the holographic limit, these correlation functions can become universal, as they must for the Rutaki-Nagy formula to make sense. The RT formula tells you that all theories in the holographic universality class, whatever that is, need to have the same entanglement entropy. And it's this fact that it reduces the stress tensor exchange that allows that to happen. Now, there are caveats here in this statement that it's universal. In some of the situations that I'll discuss, that's a precise statement with precise set of criteria. In other of the situations I'll talk about, it's a conjecture, and it needs to be understood better exactly when universality holds. So here are a couple examples where this works in some more detail. First of all, 2 intervals in the vacuum state. So if you want to calculate the entanglement entropy for 2 intervals in vacuum, you need 4 twist operators. So you have 2 intervals and 1 twist operator at each end of each interval. And the statement is that in holographic theories, this 4-point function, when you expand using the OPE, is actually dominated by stress tensor exchange, not just the stress tensor, but everything you can build out of the stress tensor. So I'm including the identity in here, the stress tensor, t squared, derivatives of t, t cubed, and so on. This is true not just, this actually includes the contributions also from other states. I'm not assuming that there are no other light states, just that there aren't too many other light states. And this is still the dominant contribution. So this was extended in this nice paper last year by Fitzpatrick, Kaplan, and Walters to excited states. In excited states, you have not only the twist operator insertions, you also have to insert some other operators that create your excited state. But again, if that state is created by local operators, you can write this as a correlation function. And the statement is that that correlation function is, again, dominated by stress tensor exchange in the holographic limit. Now, this sum over stress tensor exchanges, where you put all the stress tensor stuff in here, is by definition the Virasoro conformal block for the vacuum representation. Okay, so this wouldn't be true in higher dimensions. In higher dimensions, all the stress tensor stuff lives in different conformal families. But in 2 dimensions where we have extended conformal symmetry, Virasoro symmetry, all this stuff lives in the same conformal family, and it all organizes into a single conformal block. That's the vacuum representation. So what that means is that entanglement entropies are related to basically logs of Virasoro conformal blocks for the vacuum representation. Now, this conformal block is in general not a known function, but it turns out that in the limit that we need, large central charge and these holographic theories, Zamolodchikov gave a method to calculate it 25 years ago. The method goes something like this. I'm rephrasing it slightly. First, so this is to calculate the Virasoro vacuum block. First, you're instructed to find a flat SL2C connection in your conformal field theory manifold with defects at the interval endpoints. Second, you impose a trivial holonomy condition around your region A in that flat connection. Then there's some other steps I don't want to tell you about, which basically amount to solving a word identity to calculate the block. And the observation is that this is actually identical to constructing a 3-dimensional hyperbolic geometry and then calculating the on-shell Einstein action for that geometry. Okay? So what that means is that entanglement entropies, and therefore by Ru-Takenagi, geodesic lengths, are encoded in the Virasoro vacuum block. So again, this prescription is 25 years old, and the statement is basically that if you try to calculate entanglement entropy within this class of theories, directly in conformal field theory, you're basically going to be forced to construct holographic, to construct dual geometries. You're forced into it. Okay, so that's the method. Now I'm going to discuss some applications. So the first application is to black holes. So let's insert a primary operator at the center of the Euclidean plane. By the state operator correspondence in CFT, this creates a high-energy eigenstate on the circle. Now, in holographic theories, most high-energy eigenstates are black holes, or at least are indistinguishable from black holes. So the entanglement entropy that one computes in this high-energy eigenstate should agree with some calculation on a black hole background. So this is dual to a black hole, not the black hole thermal state that we often talk about, but to some black hole microstate. The holographic prescription to calculate the entanglement entropy in this state is to take the black hole background, find the, in this case, geodesic, since we're in 3-dimensional gravity, and compute a quarter of its area. Okay, so to check this from conformal field theory, all we need to do is take the kinematics corresponding to this state, plug them in to the Virasoro vacuum block that was calculated by Fitzpatrick, Kaplan, and Walters, and indeed, that reproduces this geodesic length on the black hole background. So this is a thermal answer coming directly out of an eigenstate calculation in conformal field theory. The second application has some simple dynamics. Okay, so that was static. Well, now let's get things moving a little bit. So in the second example, I want to inject some large amount of energy into a conformal field theory at the origin, at some local point, and then let it evolve in time. Okay, so we basically kick the system, and we let it evolve and ask how the entanglement changes with time. Well, what do we expect? Here, we're kicking the system here. That's creating some stuff that's heading out in the 2 directions. And we expect to see some signature of that in the entanglement of region A at some point as that stuff moves through the region. This is actually very similar to the black hole case. We can model this state just by inserting an operator not at the origin, but very close to the unit disk. So to get an eigenstate, we insert at the origin. That creates something that's uniform on the disk, on the circle. To get this local stuff inserted here, we insert it near the disk, and that will give us something time dependent. So this is just related by a conformal transformation to the problem solved before. On the black hole side, it's just related by boosting the black hole. So this is almost trivial, almost a trivial extension of what I just said. except that the answer is actually different because we need to be careful about operator ordering in Lorentzian signature. So when the dust settles, it turns out the entanglement entropy is computed not by the ordinary Virasoro block, but by some monodromy of the Virasoro block. So this comes from dealing with the operator ordering. So you go around you take the Virasoro block, you go around the cut, you go around through the branch cut at 1 and come back to 0, and that calculates for you the entanglement entropy after this local quench. So if you do that calculation with the Virasoro block, here's what you get. This is intuitively pretty reasonable. It's flat for a while. Region A can't see the quench at the origin. Then there's a bump as the stuff moves through region A, and then it goes back to 0 as the stuff heads off towards infinity. OK. So this agrees precisely with the holographic formula applied to boosted particle geometry or black hole geometry calculated by this group a couple years ago. OK. So the last application I want to tell you about is the thermalization. So this is an experiment called a global quench. And what that basically means is we're going to just dump a bunch of energy uniformly into the system and ask how it evolves with time. So the initial state here is a finite energy density state, but with only short distance entanglement. So one way to make a state like this is to start in the ground state of some gapped Hamiltonian. And then at t equals 0, you switch to a critical Hamiltonian and watch how the system evolves. So a useful picture to have in mind, although this is only really accurate in free theory, but it's sort of accurate otherwise, is that the quench at time 0 creates a bunch of locally entangled Bell pairs. So there's short distance entanglement, but no long distance entanglement. As time goes on, those Bell pairs will start to move apart. The entanglement will start to spread out. They keep going. Eventually, we expect this state to look thermal because everything will get all mixed up. And the question is, how does this system thermalize starting from this uncorrelated initial state? So for a single interval, the entanglement entropy of a single interval, this question was answered in CFT by Calabrese and Carty. And the answer makes a lot of sense. So the answer is that first entanglement grows linearly. That's as these correlated pairs start to move out, the entanglement entropy of region A increases. But then at some point, it saturates. And it saturates exactly at the thermal value of the entanglement entropy. So at some point, these entangled pairs have moved apart enough that everything is just completely mixed up. And locally, you can't tell the difference between this and a thermal state. So at that point, you get the thermal value, and it stops increasing. So this answer holds in any conformal field theory, whether or not it's holographic. I mean, it has been reproduced on the holographic side. But just from staring at this plot, even if I put in all the units and everything, you can't tell whether I'm talking about a theory of quantum gravity or a theory of 1,000 free bosons. They'll give the same answer. So for a more detailed probe of this system, we need to talk about more than one interval. So this goes again to the statement that entanglement is really a many-body thing, and we need to talk about more than one subsystem. So for two subsystems, A and B, the relevant quantity is the mutual information, SA plus SB minus SAB. So this is a measure of correlations between region A and region B. And we want to ask in this quench, where we just dump a bunch of energy into the system and watch it thermalize, what happens to the mutual information of regions A and B. So what do we expect? Well, in a free theory, it's going to look something like this. It's going to start out 0. That was the assumption. We're starting an initial state with no long-distance correlation at all. Then the stuff in the quench is going to head out in the two directions. And at some point, you're going to find correlated stuff in region A and region B. The stuff that was created in the middle is now going to have part of it in A and part of it in B, so we'll have some mutual information. That's this bump. Then that stuff will head off to infinity, and it'll go back to 0. So this is what happens in the free case. If you do this calculation holographically, the holographic quench, what you find is that the mutual information is completely lost. The entanglement is lost. By the time this stuff you created at the center reaches the regions A and B, you can't detect it anymore. So the holographic calculation just gives you a flat line. I'm assuming here that the size of the intervals, that the separation of the intervals is at least as big as the size of the intervals. Okay, so unlike the single interval case, there's a big difference here between free theory and holographic theory. The difference is that in free theory, entanglement doesn't scramble. If you start with a maximally entangled Bell pair, that's always going to be a maximally entangled Bell pair, no matter how long you wait, and you get entanglement at long distances that you can detect from the mutual information. Whereas in the holographic calculation, it's maximally scrambling. So in the holographic calculation, you'll just never see this mutual information that was created in the center. So we wanted to understand where these two different limits were coming from and what the general story is in between. So using methods similar to what I described, so this conformal block approach to calculating entanglement entropy, what you find is that the bump in the mutual information comes from a particular singularity in the Virasoro block, which is a singularity as the cross ratio z goes to 1. So that limit might not mean anything to you, but I can refer back to the talks this morning. This is the double Lightcon limit in the conformal bootstrap talks. So there's a particular limit in the Virasoro block in this double Lightcon limit, and that's what's responsible for this bump in the mutual information. The strength of this singularity depends on the value of the central charge, or actually on the value of the central charge compared to the number of conserved currents of your theory. So if the central charge is less than the number of conserved currents, less than or equal to the number of conserved currents, then you get back the free answer. So you get this perfect bump with no scrambling of entanglement. This holds for rational theories. It holds for free theories, and also for certain irrational theories which have an enormous number of conserved currents, like an irrational boson. So these are theories with lots of conserved currents. In a sense, they have as many conserved currents as operators, because C is measuring the spectrum, and currents is the number of currents. Okay. In the opposite limit, which is the holographic limit, C goes to infinity, combined with this sparseness assumption, you get back the holographic answer. So from this CFT calculation, you find that mutual information is completely scrambled and never seen. So entanglement scrambles maximally in these holographic two-dimensional CFTs. What about in between? So for moderate values of the central charge, say C greater than 1 but not infinity, we can give explicit examples with say C equals 6 or 12. Entanglement scrambles. If you haven't thought about quenches in two-dimensional CFT, that's probably not surprising at all to you. So it's an interacting system. Entanglement is going to sort of dissipate is going to spread through the system, and probably it should scramble. But actually, if you have thought about it, you might be a little bit surprised, because it was thought to be impossible for entanglement to scramble in two-dimensional CFT due to an argument that left and right movers factorize. So what we found from this conformal block calculation is that this logic really only works in theories that have a sufficiently large number of conserved currents, as many conserved currents as states. So we don't know if there's a condensed matter incarnation of this. It's easy to construct examples of these theories with small central charge that scramble, that are supersymmetric. But I don't know if there's something closer to condensed matter. It would be interesting to find one, because I think that these sorts of systems will behave much differently from the two-dimensional critical systems that people usually discuss. OK, so I'm going to end with just a few comments about sort of where I hope these calculations are going. So we've seen some cases where entanglement dynamics of two-dimensional CFT reproduces semi-classical gravity. Now, the methods that I described rely very heavily on Virasoro symmetry. This doesn't exist in higher dimensions. So this doesn't generalize, or at least there's no easy way to generalize this to higher dimensions. That bothers me a little, but not too much, because I think that ultimately some of the most interesting questions here are not how to get classical gravity that we already understand fairly well, but how and when geometry breaks down in quantum gravity, for example, in the context of black holes or information loss. That's a question that you can ask in 3 dimensions. So 3-dimensional gravity has black holes, it has information loss, and it has all the associated puzzles like firewalls in the black hole interior. Presumably, the answer to these puzzles in 3 dimensions is similar to the higher dimensional case. The natural place to try to answer these questions is, or a natural place anyway, is ADS-CFT. But to do this in ADS-CFT, I think we need to understand better where semi-classical geometry came from in the first place. Once we've understood that leading term as some first term in some controlled approximation, then we can start trying to poke holes in that approximation and asking where it breaks down. So I think this is definitely a difficult problem. So probably 2 dimensions and 3-dimensional gravity is a good place to start. OK, thanks very much.
Thank you very much. So, your questions, comments?
Thank you very much. It's a really beautiful talk. If I can just go back to the first part of it where you were trying to compute the mutual information or entanglement and then use this Zamolodchikov prescription and automatically got the geometry out. Just to understand, suppose instead of the entanglement, we were trying to compute a correlation function of stress energy tensor operators in the boundary theory. Again, would you see the geometry of 3 dimensions that way? Is it tied to entanglement per se?
No, it's not really tied to entanglement per se. So it's a property of heavy operators. So if you just calculate the correlation function of stress tensors and you're on a flat background, then I think that's just the Virasoro algebra. So I don't think there's really anything to find there. Now, if you calculate, say, the correlation function of some other heavy operators, then similar thing will go through. Now, you might not actually be able to do the calculation, though. So it was key here, and I sort of went over this quickly, it was key here that at the end of the day, where was that? It was key here that at the end of the day, you could take some of the operator dimensions to 0. And that's what actually allows you to get analytic answers to these formulas. Otherwise, you could find some formula in terms of the Virasoro block, but wouldn't actually be able to compute it, I think.
But if you put in the sparseness and so on, OK, the Virasoro block would close in itself, but I see. So you need the additional operators.
If you want an analytic formula, you need this.
Oh, yes.
Why in that case, I mean, I can understand that if you're, say, computing it where you have heavy operators and then you're sort of dominated by one Virasoro block, just a stress tensor block. But now you also have another light Virasoro block in the game.
So you're talking about the second one or the first one?
The second one.
So psi here is a heavy operator, actually, for these purposes.
Ah, OK. I thought.
So this is eventually what's dual to the black hole microstate.
Okay.
So it's got order C conformal dimension.
So you're still assuming that there are no other light Virasoro primaries in the theory besides the identity block, basically.
There can be other light primaries in the theory as long as there aren't too many. So it's not that we're assuming that there's a gap and no other contributions. What happens is that this is exponentially large, and including other primaries will only affect the coefficient. So even if you have other primaries, the stress tensor exchange will dominate.
Okay. Thank you.
So now?
Yeah, maybe you briefly mentioned this, but if instead of the ground state, you take a CFT in a thermal state, and just with a single interval, does this method of Virasoro blocks sort of give some insight into how you can calculate entanglement in general? CFTs?
Yeah, I think it does. There's a calculation by some folks at Stanford which did something at finite temperature, and there have been some other calculations involving perturbations at finite temperature. So yeah.
Do you know if this was at finite size also, or only at finite temperature?
There is a finite, yeah, it was a finite size. It was a calculation on the torus.
torus,
In that
okay.
case, you have to calculate conformal blocks on the torus,
Right.
which is harder, but you can do it in a series expansion.
Mhm.
More questions? Yes.
I had two questions. One was about the black hole microstate interpretation. So this changing here, you should expect the entanglement entropy for the region and its complement agree. Is that something you see in terms of the conformal blocks?
Yes, it is, and actually it happens in an interesting way. So if you just do the calculation that I described, you'll actually get the wrong answer, and you'll find that SA is not equal to SA complement. In a way, what you're doing is the same wrong answer that you might get on the gravity side by thinking this microstate is a black hole. But on the CFT side, you can correct that by including other contributions, heavy contributions to the conformal block. You could do that using crossing symmetry by basically including other channels. And when you include other channels, you'll recover the fact that it should be SA equals SA complement. So this is actually sort of a miniature version of some kind of information problem that you can do a wrong calculation in CFT and see that it breaks, and then you can fix it by including non-perturbative corrections.
And the second question was, when you showed the bump in the mutual information for two disconnected intervals, I would expect that the bump is order 1 over c in the large C expansion. Is that correct or not?
So I've certainly only talked about the leading term here. There could be 1 over c corrections. I'm actually not sure because you're in a finite energy state. So if you do this calculation in the black hole, I don't know if all that stuff, you're thinking about the matter fields, and I'm not sure if the matter fields just fall into the black hole or if they contribute. I actually don't know the answer. There could be 1 over c size bump.
Yes.
So can you just clarify what you meant about including other channels? I mean, usually you don't sum over both channels at the same time, right? I mean, you pick one and it's equal to the other one, right?
Yeah, that's right. So if you can include everything, then you should just pick one and only use that one. But if you're approximating it by some contribution of light states and ignoring the heavy states, then a reasonable thing to do is not to sum over channels, but to maximize over channels. So that's what so that's the procedure that gives back the pure state answer, SA equals SA complement. If you think of it as in a single channel, then what you should be doing is including all the heavy contributions, but we don't know how to do that. So instead, we just include the light contributions in a dual channel.
Is that somehow, intuitively, I guess I sort of see that, but is that really just,
It's justified as a bound. It's not justified to claim that that's the full answer. That's an assumption. But certainly, at least you have to have those contributions.
Okay, thank you very much. So before ending this session, there's a